So that's the point. This case has been studied in Mirzakhani and Mohammadi, and this case is different or more delicate, and everything that I will discuss is joined with non-smiles. So my plan is to, since this is a topic that's kind of complicated, my plan is to, requires lots of preliminaries. I'll tell you what the problems are, what the space is, what the Eskin-Mirzakhani-Mohammadi result is, and then describe our new results and the strategy. So the space that we study is the space of translation surfaces. So let me recall what translation surface is. It's a finite union of polygons in the plane with pairs of parallel edges glued to each other. With pairs of parallel edges of equal length identified up to an equivalence relation, which is obtained by cutting and rearranging by translations. So we had a beautiful talk yesterday by Jay Devathuria, and he showed us some pictures. So let me draw some more pictures to explain this definition. So translation surface, you can say here is a polygon. I just take a rectangle, and here's another kind of a hexagon, non-convex hexagon, and I can identify edges here, and the definition says that each edge must have a parallel edge of equal length somewhere, and these get identified. So for example, in this picture, I can identify these two, I can identify these two, and these might be the identifications. So this is one translation surface. This is such a picture, and I can impose this equivalence relation of cutting and rearranging by translation. So for example, I can add an additional cut here and get a new, I call it different presentation of the same translation surface. If I just stick in another edge and a new gluing, this is a different presentation of the same object. So that's what I mean by translation surface. And in Jadev's talk yesterday, we had an L shape. So this surface that I've drawn for you is actually the same as an L shape, which you get by sort of moving this polygon over here and removing this edge, moving this one over here, and moving this edge, we get this L with opposite sides here identified. Okay, so that's a translation surface. Now, each translation surface is defining for us as a topological object, a compact-oriented surface of a certain genus, and the curvature of these surfaces is everywhere zero. So these are flat structures, except at a finite set of points, which are called the singular points. So the singular points arise because at the vertices of the polygons, if you start traveling around the vertex, so for example, I take this vertex and I begin traveling around it, I have to follow the identifications, and then I see, first of all, that these 2 points are actually the same, and also, as I keep going, I discover that when I've gone full circle of an angle of 2 pi, I may not be back where I began, because now I'm over here, and I keep going, and I keep going, and so the total co-angle around these points is not necessarily a multiple of 2 pi, so there are there's always a multiple of 2 pi, but it's not necessarily exactly 2 pi. So there are finitely many singular points, which are points at which the total cone angle is some integer multiple of 2 pi bigger than 2 pi. These are called the singular points. So it's singular points finitely many points at which cone angle is 2 pi times k plus 1, where k is a positive integer. And so this is a translation surface, and there's an action, there's a space of all translation surfaces, which I will describe in a minute, and there's an action of the group SL2R on translation surfaces. It's easier to describe the action. The action is just take such a presentation in terms of polygons and just apply the linear action of the matrix on the plane. You get a new finite set of polygons satisfying the same definition, so you get a new translation surface. That's it. That's the action. And it's clear that this action respects this equivalence relation, and therefore it's a well-defined action.
So every edge must be identified with precisely one edge, precisely one other.
Yeah. Every edge must have someone to pair with, exactly one edge to pair with, and the identification must be given. So, for example, in this picture, these two edges are parallel, and these two edges are parallel. Part of the structure is to say what the identification is. Okay, so I want to define the space of translation surfaces. The space of translation surfaces, or in other words, I want to give a topology on the set of all possible translation surfaces. One way to do this, as Jadeb was describing yesterday, a translation surface is also equivalently given by a holomorphic one form and a Riemann surface structure. So you could just think of translation surfaces as a certain bundle over the bundle of holomorphic one forms over the moduli space of Riemann surfaces, and that will give the same topology, or that will give a similar topology to the one that I'm describing with some nuances. But I don't want to use this language of Teichmuller theory. I'd rather give you a concrete description of the topology from these pictures. So one thing that you can do to a picture like this is to perturb a picture, which means that I can slightly move the edges, maintaining the relationship of being parallel. So for example, I could let me find a good perturbation. I can move this, replace this edge by some edge which is rather close to it, but a little bit different. Do the same thing to all parallel edges, and I get a new polygon, a new system of polygons, which is slightly perturbed, and which still defines the translation surface. And all such perturbations are going to give rise to the neighborhood of this original translation surface. So this is like a very natural topology. And so this is called, and in this perturbation, the number of singular points and the cone angles around the singular points are preserved. And since we're interested in the SL2R action, we notice that also the SL2R action preserves the number of singular points and the cone angle around the singular point. So we are going to restrict our attention to a situation in which we have a fixed number of singular points and a fixed collection of cone angles. So a fixed number, fixed certain set sigma, which is the finite set of singular points. Fixed cone angle at each point of sigma. And this gives rise to a space which we denote by H, and let's just fix S to be the topological isomorphism homomorphism class of the surface. So that's just a fancy way of saying that we fix the genus of the surface. And then we get a stratum, which I denote by this letter scriptal, which is all the
cone angles is part of the data.
Yes, well, it's when I'm describing the space, I have to fix the data. Yes.
But then is it asymptotic invariant?
Yeah, I just said it is asymptotic. If you think of it, if we are given a presentation and we act by SL2R, we have the same vertices of the polygons, and when we follow the
but the angles are
yeah, the total angle is preserved because
total angle.
Yeah, the total angle around a singular point is preserved. It's like perturbing the tangent space to a point in a branch cover construction. So the point is fixed and a number of times. Let's put it this way, it's a continuous deformation and it's a discrete parameter, so certainly it has nothing to do. Okay? So H will be all translation surfaces with these with singularities. All translation surfaces, sorry, homeomorphic. To S, singularities indexed by sigma with prescribed cone angles. Which means I fix at each point of sigma, I fix the cone angle at that point. So there are infinitely many strata, one for each choice of these possibilities. And SL2R acts, and now I want to topologize this space. And in order to topologize this space, I note the following. If I have such a translation surface, I can use the planar structure, or the planar structure here, to integrate paths. So in other words, if I take a path in this picture, for example, I can take a path, this is what was also in David's talk yesterday. For example, I can take a path from this point to this point, passing through the picture in this way. And using the planar structure, I can associate to this path a vector in the plane, which is just the x and the y, the difference in the x and the y coordinates taken by this path. So that's a vector in the plane. So for any M will be my generic letter for a translation surface. For any translation surface M and any path connecting points of sigma, the holonomy, let's call the path gamma. The holonomy, according to M of gamma, is a vector in the plane, which gives us the x and y coordinates of this path with respect to the planar structure. The paths are oriented, I should say. Good. And so we get a map from surfaces to where you can check that this holonomy only depends on the homotopy class of gamma. In fact, only depends on the homology class of gamma as one relative one cycle in the homology group. In this homology group. Okay? Let me say that again. H1 S comma sigma is the first homology group of the surface relative to this finite set sigma. So this is just cycles either closed in S or joining points of sigma. And each such cycle can be integrated using the planar structure. And it turns out that the plane, this is well defined. In other words, if I integrate two homologous paths, I get the same vector. So this holonomy is a mapping of this form. And in fact, the holonomy also vanishes on boundaries. So in fact, the holonomy is an element of the homology group, of the cohomology group, taking coefficients in R2. So given a translation surface, I can find an element of the first cohomology group of S relative to sigma with coefficients in the plane. And with this language, I can define something which is called a developing map sometimes. So we're getting a map from the stratum to the first homology group. But this map, there's many such maps. I mean, this map depends on the identification that I make between this homology space and my picture. So given a picture of the surface as a union of polygons, I have to identify the picture with my surface and say where the points in sigma are. And there are many possible ways of doing that. I can apply, having fixed one such identification, I can apply find another identification by applying a homeomorphism of the surface fixed in sigma. But having fixed a translation surface and having fixed such an identification, I get this map. And the theorem is that this map is a local homeomorphism. In other words, this map gives H the structure of a manifold. It gives a neighborhood of a point in H. It maps it bijectively with a neighborhood of a cocycle in this cohomology group. So this is so we can topologize H so that dev is a local homomorphism. And once I've said that, I should explain to you how SL2R is acting in these coordinates. So this is a coordinate system on H, and in this coordinate system, SL2R just acts on the plane in this cohomology space, because when you have an action on the coefficient ring of homology space, you have an action on the cohomology space. So in other words, if I another way of saying this is if I take dev of GM, which is the image of M under the SL2R action by an element of G, this is the same as dev of M, which is a cocycle taking values in R2 composed with G as a linear map. Okay, so it's a very simple action. And another important feature, which will be very important for what follows here, is not only does this topologize the stratum and give it a manifold structure, it actually gives it a linear manifold structure. There's a linear structure. This is a vector space. And every structure on the vector space which will be preserved by the transition maps of this atlas, I'm telling you about an atlas of charts from the stratum to a vector space. Every structure that's preserved by the transition maps of this atlas will be a well-defined structure on the stratum. Okay, so what is the atlas? As I said earlier, this is not just one map. Dev is not one map. There are several maps, countably many maps, arising from taking different identifications of my model surface S with my translation surface. And changing the map just amounts to applying a linear map on the homology space. Okay, so if we change the identification of M with S sigma by composing homeomorphism. H of S fixed sigma dev of M changes by linear automorphism of H1. It's just by the linear automorphism H lower star. Right?
You are rotating the polygon?
No. As I said, I fix a model surface. So fix a surface, topological, just some kind of topological surface somewhere. Whenever I have and fix a finite set of points on it, say 2. Whenever I have a translation surface of this genus and this number of points, that gives me a surface which is homeomorphic to this. But the homeomorphism is not unique. There may be several homeomorphisms of my translation. For example, the translation surface could be, say some picture like that. Okay, this is homeomorphic. I have a picture like this, which is a translation surface, which I know is homeomorphic to this surface. So any path here is identified with some path here, but I need to make an a priori identification of the translation surface with my model in order to discuss the homology space.
Because you are changing your identification in the translation surface itself.
Pardon?
So you are changing your identification.
Right. So when I change this identification, that's known as changing the marking. That two markings of the same translation surface differ by a homeomorphism of sigma of S fixing sigma. So we have you can think of a map here which fixes sigma and is a homeomorphism of the surface, and that will change this identification. So it will change this this cocycle, and the change in the cocycle is given by just the map, the effect of the homeomorphism on this homology group, a linear map.
What is the dimension of this H1?
The dimension depends on the number of points in sigma and the genus of S, so it's 2g minus 2 plus
2g plus n minus 1, or n is
2g plus n minus 1. N is the number of singular points. 2g is the dimension of the absolute homology. And if I add n singular points, I'm adding n minus 1 to the dimension. It's 2g plus n minus 1.
It's different from the tabular space.
It's different from the tabular space. The tabular space you should think of, in the tabular space there's no canonical choice of sigma. So different sigmas give us, this is the reason it's called a stratum, is we're sort of stratifying the bundle of holomorphic one forms, which has a dimension which is well known in complex analysis.
And another of this
We're
would be
stratifying
the space with some points marked.
Yeah, we're marking this set sigma.
It is 3g minus 3 plus n.
The way you can think about it,
No.
this is a bundle over tabular space.
Well, no, each individual stratum is not necessarily a bundle.
But if you, for instance, if you say n is 2g minus 2, if you look at the sort of the most generic one, that is a bundle over
Right.
tabular space.
Let's put it this way: take the total space of Teichmüller space and take the unit tangent bundle to Teichmüller space. Okay, so Teichmüller space is 3g minus 3, tangent space is 6g minus 6. Right? The tangent space to Teichmüller space can be identified with what are known as quadratic differentials, which are essentially this kind of structure, but you also need to allow for rotations by 180 degrees. And this tangent space to Teichmüller space is stratified, so it's a union of finitely many subvarieties or submanifolds of varying dimensions, and the dimensions depend on the choice of this set sigma, which you should think of as the set of zeros of the quadratic differential, and the total cone angle around these zeros. So you're getting a decomposition of the unit tangent bundle, the type of the space, into pieces, which are these strata. Okay, so this is what I'm stressing here actually is that these strata have a natural linear structure. Okay, so they have a topology, but they also have a natural notion of a linear structure. It's not a vector space, but it's locally modeled on a vector space. So the notion of a linear submanifold is a well-defined notion. A submanifold of a stratum is called linear if in every atlas in this chart it's a linear submanifold. That's important for stating the results of Eskin and Mizukani. So this, I'm bundling together to save time two theorems into one. So there's a theorem of Eskin-Mirzakani, and there's a separate theorem of Eskin-Mirzakani-Mohammadi. These are two big and very important papers. And the theorem says the following: any G-invariant ergodic measure on H is obtained from the Weg measure on an invariant linear manifold, linear submanifold, via the cone construction. I'll define the cone construction in a second. This is what you might call the counterpart of the Ratner measure theorem, and the counterpart of the orbit closure theorem is that any G orbit closure is the supportive supermeasure. So this is the kind of situation for G. I need to tell you what a linear, what the cone construction is. So another invariant.
G.
G is SL2R throughout the cone. G is SL2R, and U is the arbitrary input group. And I need to tell you what the cone construction is. So this is a linear manifold. So a linear manifold, in every chart there's a special point which is 0, the identity of the vector space, because transition maps are linear maps. So that's a well-defined notion. So when you have a vector space and you have 0 somewhere, you can do the following construction. So here's you can take a subset of a vector space, suppose it's a codimension one subset, and 0 is over here. You can form the cone over this set, which is the union of segments from the set to the identity, and you can measure it for Weg measure. Okay? So if we have a codimension 1 subvariety of a linear space, we can measure sets on the codimension 1 subvariety via this kind of construction. Okay? For this action, there's a natural codimension 1 invariant subspace, which is the set of area 1 surfaces. If you fix the area of a surface, that's an invariant of the SL2R action. So in the stratum, there's a distinguished subset, which is the set of surfaces of area 1. And this problem of understanding invariant measures naturally reduces the problem of understanding invariant measures on surfaces of area 1. And the theorem tells you that all you have to look at is to identify the linear submanifolds in the stratum, which are invariant under SL2R and closed. Take the Weg measure and code it off, and you get, by this cone construction, you get these measures. So in other words, in charts, the invariant measures and the orbit closures are supported on subsets which are given by linear equations and one additional equation, which is the area equation, which is a quadratic equation. It's determined equals one type of equation, and in local charts, this looks like a quadratic equation. So the upshot here is invariant measures on closed sets cut out by linear equations plus one quadratic equation, one quadratic equation. It's the area one condition of the quadratic equation. Okay, what are our results for the U action? So this is the content of our work. We have two families of examples. The first, so the question is, what about the U action? And we have two types of examples. In the first type of examples, we have, so there are U invariant ergodic measures whose supports are linear manifolds with boundary and with infinitely generated fundamental groups. So the two novel pieces here for the U action are, first of all, that these manifolds may have boundary, which never happens in the SL2R situation. These are manifolds without boundary. Also, it's known that the manifolds constructed in the Eskin, there are some restrictions about these Eskin-Mirzakhani-Mohammadi submanifolds, and I would say that's probably a theorem, but at least to be safe, it's very widely believed that you cannot have this phenomenon of having an infinitely generated fundamental group. So that's the first. I mean, actually, I think it's already been proven, maybe Jane knows, or certainly people are discussing whether these manifolds that arise are algebraic varieties.
Wait. But if you have, oh, they're not closed, right? I was thinking of the page groups, but the SL2R is not closed, right?
So it's widely believed that the manifolds, the linear manifolds which arise in the Eskin-Mirzakhani result are never sufficiently complicated as to have infinitely generated fundamental group. And the second type of example here is that there are it's the same U invariant ergodic measures whose supports are not obtained. Which are not obtained from the Weg measure on linear manifolds. By a Cohen construction, and these guys locally satisfy two nonlinear quadratic equations. So the point of the second example is that we leave the world of manifolds which are linear except for the area 1 restriction. We get sets. We don't know actually that these are manifolds at present, but we do know that if they were manifolds, then they would have to be cut out by linear equations and two independent quadratic equations. Okay? So locally they look like more complicated manifolds if they ever did that. In some areas they are manifolds, in some subsets of them they are manifolds, and the manifolds have like two quadratic equations. Okay, that's the those are the results. So I want to tell you, kind of hand wave you a little bit through the strategy involved in constructing these examples. And depending on time, we'll see how much detail I can give you. But I can give you the basic strategy. The basic strategy for examples of type 1 is simpler than the basic strategy for examples of type 2. So I'll start with the basic strategy for the examples of type 1. And this strategy has been used before in work of Calton and Workman. First Calton's thesis, Calton was speaking of Eskin, first Calton's thesis, and then another paper of Calton and Workman. And we pushed the strategy a little bit further. So here's what we do in this strategy. So suppose we have a vector field on H. Vector field on H just means the choice of a point at each tangent space. It's a vector field, so at each point of in H we choose a vector in the tangent space, which commutes with the U action. So what I mean by that is that just that the Lie bracket of the infinitesimal generator of the U action and this vector field commute. Or another way of thinking about it, if there was a way to integrate this vector field to form a group action, to form a one-parameter group action, then these two actions would commute. Okay? So whenever one group commutes with another group, and you have a measure invariant on the first group, you can push it forward with the second group to get a new measure. Obviously, it's a very easy trick. That's what's called acting by the centralizer, a very standard trick in say, homogeneous dynamics. Here, the centralizer is not a group, it's a vector field. It's an infinitesimal thing. And the question of to what extent this infinitesimal action integrates to a globally defined action is quite tricky. But the vector fields themselves do exist. So we can, so given parameter t, can push forward points of distance t along the vector field. This gives us a map. Let's call it psi of t from a certain subset of H into H, where if the vector field is not complete, then this won't be the entire stratum. And the vector field that we discuss, the vector fields that we are discussing will not be complete. So if H, so H0 is the subset of H, where the where this notion is well defined. And if mu is U-ergodic and invariant, and gives full support, gives full mass to H0, then the push forward of mu by Ct is a new ergodic invariant measure. that's exactly what we find. There are such vector fields on the stratum. If you move along these vector fields, you may fall off the stratum. In other words, if you have a developing map into this homology space. In the homology space, this vector field gives rise to just a linear, just a line, just an infinite line. As you travel along this line, you stay in the stratum for a while. You may fall out of the stratum. We just said that the stratum is locally modeled on this vector space, but maybe not globally. And if you don't, then this operation, this line in the homology group lifts to a line in the stratum. You just move along the line to distance t, and that's what I call psi sub t. So for every t, we have a push forward operation to distance t, and we get a one parameter family of measures if we can verify this condition. And this is exactly what we do.
H naught depends on T.
H naught may depend on t. In fact, H naught, in our examples, there's always a subset of H naught which always has a full measure, which is independent of t. And then there's some additional stuff which may depend on t. Okay? And where's the boundary? So I said that this linear manifold has boundary, and it has an infinite generated fundamental group. So let me sort of wave my hands and explain to you where the boundary is coming from and where the infinite generated fundamental group is coming from. The boundary is just the set of points in the complement of H0. So actually what happens is the set of points where this operation is not defined can be explicitly identified, and the set of points is a submanifold, and you just pull out the submanifold and you get a boundary. So you're getting you start with a nice measure, nice support on a manifold, as in the Eskin measure kind of paper. You remove a subvariety of positive codimension where this operation is not defined. The complement of this subvariety is a manifold with boundary. Then you push it forward under T. And what happens is, as I push the manifold forward, it cannot be continuously completed to the part that you remove. The part that you remove sort of moves in two different. You've removed something, and then the manifold pushes in two different ways. It's just like an interval exchange transformation hitting near a singularity. You push it forward, and then it goes two different places, and that creates the image of the map. That creates the boundary. Where is this infinite generation coming from? Actually, what happens is the thing that you're removing is a cylinder, and on the cylinder, parts of it, after you push them forward, they move away from each other, and then they come back and reattach. So actually, the cylinder looks like infinitely many cylinders, and on some pieces, the thing reattaches, and some pieces are left hanging, so you get infinitely many pieces which are boundary components. The boundary has infinitely many connected components, and each of these connected components looks like a cylinder, and you can use that to prove this property of fundamental. Okay, that's the first. That's
So even for small t, H naught may not be equal to H.
even for small t, it will never be equal to H, actually. And this phenomenon of having boundary and having infinitely generated fundamental group will always happen even for very, very small t. The strategy for part 2 is similar but more involved. Suppose we don't have a well-defined vector field, but we have a well-defined finite probability measure on the tangent space, which is invariant for the what we call the monodromy action. So let me write it down and explain. Suppose theta is, so for every, let's write this form, theta of x in H is a family of measures, probability measures. Theta x is on the tangent space to the stratum at H. So in other words, I'm picking out probability measures worth of directions on the tangent space, such that first is that theta, this family, is, I'll write down mapping class B invariant and I'll explain what that means. So, okay,
What's theta x and h? Sorry, yeah, sorry, thanks.
let me first write down all the properties that we want, and then I'll explain. So there is a G invariant measure mu such that for mu almost every x, theta x and theta x almost every v commutes with the first well, and motion. Sorry, alcoholic fixed T such that and motion along this vector field V is well defined. So I have a tangent space. On a tangent space, there are directions. Directions can be thought of as picking out a direction can be thought of as picking out a vector field. But suppose I can't pick out a vector field in a nice invariant way. Invariant way means a way which is locally well defined on my strata. But suppose there does exist a distribution of a measure on tangent vectors which is invariant under the mapping class group action. In other words, it is well defined on my strata. Okay? Then I can do the average by theta x of this pushing forward operation. Every element of this push forward commutes with u, so the total measure commutes with u. Yeah. And if we analyze the situation, we can first of all find such examples of such measures which are non-trivial, and also prove that the resulting measure will be ergodic for the horocycle action. And yeah, let me just finish that sentence. So what we're trying to do is define